Well, guys, here we are. We're progressing along the way in Chapter 4. We're dealing with Chapter 4, Section 4, solution sets to functions with two variables. We got to think about this. What are solution sets? Solution sets are when we have an x and we plug it in and we have a y. Together, they make a solution set, which is actually an ordered pair. So there's two ways that we can express these solution sets. The first way, which sometimes is actually less accurate, is computationally. And we think about that. Well, I mean, Mr. C, think about it. If you're plugging in an exact number and you're solving, how isn't that more accurate? Well, how many possible numbers could you plug into that equation? I mean, most equations have an endless amount. Are you actually going to sit there and manually compute every single possible number we could have? So no, you're not. I mean, usually we're just going to go through and end up computing a couple of different values and throw it onto a graph. That's why graphically is a visual way. We can do that. We can use the computational way, get a couple of values or a couple of ordered pairs, put them on a graph, and all of a sudden we visually see an actual picture of what this function or this equation should look like. What we'll really notice is in the next section, we can determine if that equation really is a function or not. So again, graphically is obviously a better way to see all possible solutions. Given that, what numbers can you plug in? So x, the independents, the inputs, this all has to do with what we're putting into these equations. Depending on what the equation is, we may not be able to plug any number in. Think about equations that deal with time. Time is never a negative number. So negative numbers wouldn't make sense in an equation that is dealing with only time. Same thing with a lot of different circumstances. Money, some money problems, negative would not make sense. So you may not have all of your values be used. So we sometimes restrict these. And so depending on what you can and cannot plug in, if there is a restriction, we have domains. Domains, all possible x's. Inputs, independent variables. Or we may have ranges that are restricted, right? Which means our outputs, our y's, are dependent variables. There may be restrictions, but when we're doing equations, we need to look at them, especially if they give us a graph, and we can determine, well, what values or what intervals of these x's were used, what values, what intervals of the y's are used. And there are, of course, different types of graphs, and we have talked about some of these where we can represent this, right? Some of them are called discrete, some are called continuous. I love using this one because although it kind of seems a little gross, it really sticks the point in your head. Pet shops that sell pets, puppies, if they're doing their cost, like what they're selling by cost, right? They're selling puppies. So notice how this graph is dotted, right? We have dotted graph. Each dot is something of value. A puppy. If they sell no puppies, they make no money. They sell one puppy, they made 100. They sell two puppies, they made 200. They sold 3 puppies, they made 400. Nowhere is there a pet store that is going to sell you a half a puppy. So that's why this line is not, all these dots are not connected. The individual dots are what have value and what have meaning. Consider something different. You go to the grocery store to buy oranges, right? You're putting oranges in your bag and you put it on the scale. Will the grocery store sell you 2.5 pounds of oranges? 3.5 pounds, 3 3/4 pounds? Yeah. So this is something that's why we would make the line continuous, because even the lines in between where we might have points on this graph, they all have meaning. You could sell any value of x when it comes to if it's pounds. 1 pound, 1/4 pound, 3/4 pound, and any increment in between. Another gas for your car. Think about if if this x-axis, this independent axis, was gasoline by the gallon, the pumps can pump any increment of a gallon. So that would be a continuous line. That's why it's a continuous graph. Now, some of our examples we have is they're going to want us to be able to graph a line and then determine, well, is this line or is this value, what is the domain, what is the range of this particular graph? And we need to be able to manually do this, right? So the first thing you have to do is create a t-chart. And I don't need a lot of points to do these. Here's one I'm going to pick 0, and I'll pick 3. Okay? When x is 0, so I'm going to remove the x. I'm going to plug a 0 in. Right? So 0 plus y, well, the 0 goes away. There's nothing to do with it. So y equals 0. That's always our friend. It's the easiest one. I'm going to remove the x again. I'm going to take where the x was. I'm going to plug in a 3. I'm going to evaluate. Well, 3 plus y. I can't do that. I'm going to solve the equation because I need y by itself. Subtract 3 from both sides. Y is equal to -3. Right? So here, if I were to put this on a graph, I have the point 0, 0. I have the point 1, 2, 3. And so this line goes up in this direction forever and ever and ever, meaning if I'm here, it's going to be, a point would be here, right? And I can keep going. So if you look at your domain first, our domain, every x this way is going to be used. Because so as far as I can go, there's going to be a point that can go up. Every x in this direction can be used. So is there any x's that I can exclude? No. So I can say this is going to be all real numbers. All real numbers. And then what about the range? Let's look at the graph carefully. Look at our range. Our range, again, range deals with the y's. Okay, so if I can go in this direction forever, that means there will always be a number I can go up to that line. Go up here, it'll be way up here. Go way over here, it'll be way up here. Same this way. So again, our range is the exact same thing. And sometimes, guys, we can write it like this because, you know, as math people, we like to find shortcuts. And R with a capital R with a double line means all real numbers. They both mean the same thing. Look at this one. Now this is interesting, tricky. They gave us an equation that we haven't solved a lot of, right? 2x squared plus 3. I'm going to pick 3 numbers for this. I'm picking a range of numbers. Negative, a positive, 0. They're all ones that are easy to calculate, right? I need to plug in this. So we have 2, remove the x, squared, plus 3. I'm plugging in a -1. So -1 squared, because order of operations tells us to take care of this first. -1 squared. -1 times -1 is a positive 1. And 1 times 2 is 2. 2 plus 3 is 5. Great. I'm going to evaluate it again. So this we're going to have to evaluate 3 times. I'm going to remove my -1. I'm going to plug in 0. Okay, so 0 squared is 0. 0 times 2 is 0. And 0 plus 3 gives me a 3. So there's another point. Can erase. And we have to do it one more time. All right, here we go. One more time. We're plugging in a 1. 1 squared is 1. Notice how I'm rewriting every step so I'm not forgetting anything along the way. I'm not messing up my evaluations. This is not where we want to make a mistake. 1 times 2 is 2. And then we bring down a 3. And 2 plus 3 is 3. Oh, no. That's horrible math. 2 plus 3 is 5. Yeah, that's much better. It's been a long day at school today, you can tell. All right, so now we have to put these points onto our graph. So our first point is the point -1, 5. So we go to the left one and we go up 5. 0, 3. 0, 1, 2, 3. 1, 5. 1, 2, 3, 4, 5. Wow, this is a graph we're going to learn a lot about later on. This is a really skinny U-shaped graph. So this graph is going up in this direction and slowly getting bigger and bigger and wider and wider and wider and wider forever and ever and ever in the left direction. And it gets bigger and bigger and bigger on the right hand side. So if we were looking for the domain, our domain, again, we're using every single x there is. We can say it's all real numbers, and I'm going to use that little abbreviation again. Remember this, all real numbers means all real numbers, the double R, R with the double legs, all real numbers. But my range is going to be different this time. Notice, range deals with the y values, or y's that are being used. Is there any y's being used down here? No. Look, it seems like no matter what we do, the lowest point on this graph is this point right here, 0, 3. Is there any y that's going to be lower than 3? No. If I come out here, this point would probably be up about here. And this point here would be up about here. So somewhere in between here would fall about here. In between here, here, right? What we need to start looking at is all the y's are being used, what? Above. Because this is a minimum point in this U-shaped graph. All our y's, look, our y that's being used here is 3. Nothing's less than 3. So the y's that are being used, every y is going to be greater than 3. And like that, you're able to say there's the domain and there's the range. This problem is similar, but slightly different. They are giving us a specific set of domains. They want to know what is the range if the domain is 3, if the domain is 2, if the domain is 4. So what they want us to do is, what are those unique y's? We're going to have a solution set at the very bottom of this. Right? And we have to actually evaluate this equation 3 times. So we remove the x squared minus 2. Remove the x squared minus 2. Do it one more time. Remove the x, square it, minus 2. And we're going to plug in a 2 and evaluate. We're going to plug in 3 and evaluate. We're going to plug in a 4 and evaluate. Okay, so 2 squared is 4. 4 minus 2 is 2. There's one of our possible domains. 3 squared is 9 minus 2, and 9 minus 2 is 7. There's another one of our domain. I'm sorry, the range, because they gave us the domain, plugging it in and solving for our range. And then the last one here is what? We're plugging in a 4. So we have a 4 squared is 16. You subtract 2. 16 minus 2 gives us 14. So if the domain was a 4, the range or the output becomes a 14. And our last example is the same thing, only it's even different. We've never seen this. This is a cubic function, but it's okay. Again, we just have to write it 3 times. Remove the x, put a set of parentheses. There's a negative there. Remove the x, set of parentheses. Remove the x, set of parentheses. This is how we speed up our math. I know that evaluating equations is not fun. Nobody likes doing it, but we have to. And if we just know, remove the x, put a set of parentheses, do it 3 times in a row, and then you can just plug things in and go. All right, there's the -1, there's the 0, and I think I wrote -1 in there twice. I guess make that a +1 so that we have 3 sets. Okay, so look at this. We're going to eventually, we'll find our range from this once we evaluate it. And all you have to do is evaluate it. So you guys try that now, pause the video and give it a shot. When they gave you that specific domain, what is the range that you end up coming out with? All right, thanks for pausing the video. -1 cubed, so that's -1 times -1 times -1. Yeah, a negative times a negative is a positive. Positive times a negative gives us a -1. But remember, we had this negative outside the parentheses. That's why those parentheses were important. So one more time, a negative times a negative becomes a positive. There we go. 0 cubed. Well, 0 times 0 times 0 is just 0. So when you plug 0 in, your result is just a 0. +1 cubed. 1 times 1 times 1 is 1 in a set of parentheses. Oh, there's that pesky negative again. Remember, if you didn't put this set of parentheses, chances are you might make a mistake. That's why we had this as an example. All right, so look, there we go. And as we do this, we ended up having -1. So when our given domain, and I'm going to change that to, again, a +1. I must have typed the wrong thing there. When our given domain was -1, 0, and a +1, the range that came out of that specific restricted domain gives you 1, 0, and -1. And like that, you've learned to start to identify domain and range, and even more specifically, what is a specific domain and range if they restrict your inputs or your outputs. All right, get out there, do your homework, and make sure you finish it all up. Have a good one.